So we are going to look at function notation. So in the previous lesson, we looked at what a function is, and now we're going to see the notation that goes with it. So yeah, you should have hopefully looked at the Desmos with turtles, and we'll see that a little bit more in the future as well. But we'll just skip through that. And let's just go through a quick couple examples of what a function or not a function is. So if we're looking at the blue graph there, we want to determine is it a function or not. What we need to remember, if we have a graph, we want to see does it pass the vertical line test. And if you look at this portion right here, well, that does not pass the vertical line test because you have multiple points crossing that vertical line. So that is just a relation. All functions are relations, but not every relation is a function. In comparison, though, with the red one, wherever you draw a vertical line, each vertical line only crosses that red graph once, so it is a function. Another way that we can think of a function is for every x value, there is only one y value associated with it. So each x goes to one y. All right, and another way of thinking about x's and y's is to think of x as the independent variable. It's the thing that we're changing. And the y as the dependent variable, the thing that is going to respond to the independent variable. You can think of it kind of like a science experiment. Maybe your experiment is looking at a reaction depending on how much of some kind of product. Maybe it's like, oh, if I put this much baking powder in with the vinegar, how much is this going to react? So the x would be how much baking powder, the y would be how large the reaction is. Okay, and so now we want to get into notation. How do we actually put x's and y's and kind of describe it in terms of something being a function? Okay, and again, why do we even care about functions? Like relations, you've worked with them. We never talked about functions before, but specifically it is because of the idea of that a single input, x value, gives you a single output. That's really key. And we want to be able to use that to create models, and then those models we can use to analyze all sorts of different situations. So for example, if we're looking at the weather, we want to create a model, but we want our model to say like, oh, given these conditions, the weather person would, of course, have the information for that. It'll output something like the temperature or the humidity, whatever you're specifically looking at. But for each specific input, you have a single output. It wouldn't make sense for them to output 5 different temperatures and then you're just picking and choosing the temperature. Typically, you'll have like the temperature high for the day and the temperature low. 2 different things, but there's only one single high for the day. There's only one single low temperature for the day. So each input has a single output. And there's all sorts of different areas where we want that kind of thing, a model where we put in some value and we get out a single value in the end. And so then how we're going to create our function notation is, well, since we're dealing with this thing called a function, we're just going to typically use the letter F, and you can actually really use any letter, but we're going to start with that. And then inside of brackets, we're going to have, well, what do we do with a function? We have a single x, or we have a single input. And so that's what goes inside the function notation. Inside the brackets is our input. We start with x because typically our equations are in terms of x, like y equal to 3x squared, or below is y equal to x squared. It's a typical quadratic equation there. But now, instead of having things in terms of y equal to, we can now say f of x is how we're going to say it, or f at x. And so then what's inside your brackets is going to be the thing that you plug into your function, or you replace the x with. So let's see that at work below. So if I have f of x equal to 2x plus 1, So we have f of x equal to 2x plus 1. I'm just going to rewrite this down below. Now, if we rewrite that with a 3 inside the brackets, so the 3 inside the brackets, whatever's inside the brackets is what you're inputting, that's your input, the inside of the brackets, into your function. Well, the function is 2x plus 1. So for x, we now replace it with 3. And so it's just 2 times 3 plus 1, which is just 7. So that's the key thing. The brackets tell us our input. Typically, we start with an x for the general function, basically. And then when we're actually wanting to get a specific output, well, we need to input a specific number. So g of 3 will just be, well, since g of x is x minus 2 squared, g of 3 will be 3 minus 2 squared, which would be 1 squared, which is just 1. And you can combine function notation with each other. So if I have f of 6 minus g of 0, well, that would just be, well, I'll start with f of 6. I'll just put that in brackets first. I just have to remind myself what the function is. 2x plus 1 will be 2 times 6 plus 1. So that is f of 6 there. And then we want to subtract g of 0, so let's just write g of 0 beside it, and then we'll subtract it. And g of 0, well, g of x was x minus 2 squared, so now it's just going to be 0 minus 2 squared. And now we can just kind of separately calculate them. 2 times 6 plus 1 is 13 minus negative 2 squared. And just be careful about the negative 2. That's going to become positive. And so in the end, you get 9. And you can combine it with just regular calculation. So g of negative 1 would just be negative 1 minus 2 squared. And then we can still just have this minus 3 is outside the brackets. So that's the key thing here. You have one thing inside the brackets, which gets plugged in, and one thing outside the brackets, which is just to the side, separate. And so we subtract 3. So we get negative 3 squared minus 3. 9 minus 3, which is 6. All right, continuing on. So again, kind of the key thing with this function notation is whatever's inside the brackets is what you substitute in. Here it says f of 8 minus f of 6. Try it out yourself first. Pause the video, and then I'll go through it. Okay, so going through this, I'll just write it out as two separate things, f of 8, f of 6, then we can do the subtraction. If you have multiple x's, well, all you have to do is plug in the corresponding number, let's say 8, into both of those spots where x is. So 8 cubed, because it's x cubed, 8 squared, because it's x squared. 8 cubed plus 8 squared. Go ahead, calculate that out. And then you do the same thing with 6. 6 cubed plus 6 squared. Okay, so I've got those written down. Now let's calculate it. Okay, so we should get 576. And then 6 cubed plus 6 squared is going to be 252. And just adding the 2, subtracting f of 8 minus f of 6 is just going to be 576 minus 252, which in the end gives you 324. Okay. So again, I encourage you to try this out first yourself and then watch the answer. But try it out yourself by pausing the video. Okay, so f of c plus 2. This might look a little different, but we just need to use the same sort of idea as we've been using before. Whatever is inside the bracket, in this case it's c plus 2, plug into your function. So it feels odd because it's not just a single thing. And in fact, it's not just a number, it's a variable in there. But again, just replace x with whatever's there. So now wherever I see x for f of x, replace it with c plus 2. So it's c plus 2 squared minus 3 times c plus 2. And well, this is something that you can simplify. So I'm going to go ahead and square c plus 2. So that will just be c squared. Well, here, I'll do it the long way. Let's just write it out as c plus 2 times c plus 2. And then c gets multiplied by everything in the second set of brackets, and 2 gets multiplied by everything in the second set of brackets. It's like distribution, but you're just distributing each term in the first set of brackets by the second brackets. So you get c squared plus 2c plus 2c plus 2 times 2, which is 4, minus, and then let's distribute the last part, 3 and a 6. So minus 3c minus 6. And then just combine your terms, your like terms. So c squared, there's nothing like that. 2c and 2c minus a 3c leaves you with a single c. And then 4 minus 6 leaves you with minus 2. Okay. This next one, so we have we want to determine the value of x such that g of x is equal to 7. So let's just rewrite g of x down here. 2x minus 1. And this is a little bit of a different question because now I want to figure out, well, what would I need to substitute into the function? In this case, it's the function labeled g. It's okay, you can use different letters for the function. And we're going to see functions labeled g a lot. We want to make sure it's equal to 7. So if I have g of x equal to 2x minus 1, essentially all I'm doing here is now we're setting g of x equal to 7. As in the left side, or what would normally have been y, we're setting that equal to 7. So it's going to be 7 equal to 2x minus 1. But this is just an equation that we can solve for x. So just rearrange, move the 1 over, which will become 8. Divide by 2. And so 8 divided by 2 is 4. So therefore, if x equals to 4, g of 4 is going to be equal to 7. Or just go ahead and check that out. When you plug in for 2x minus 1, 2 times 4 is 8, minus 1 is 7. All right, and since we're looking at functions, we're looking at relations, we can always take a look at their graphs. And let's keep in mind what these actually mean. So a graph just gives you x and y's. And now we're looking at things f of x. But we can keep in mind that f of x is just a representation, essentially, of the y value. So your answer is the y value, or is the output the y coordinate. The input is your x coordinate. So what this is saying here is f of 3, if I want to determine what that is equal to. So what is the y coordinate? That's what I'm looking for. Well, that means x is equal to 3, so just find the point that has x equal to 3. So x is equal to 3 right there, and the corresponding y value is 4. Or the point is 3, 4. So f of 3 is equal to 4, therefore. Okay, in a similar way, we can do the same with f of 5. So if we take a look at the graph, go to 5, and we can see that, okay, it's that point of the graph there, and what's the y value of that point? It's 2. So that's the point 2, 5. So 5 is the answer. So f of 5, or sorry, I switched my coordinates around there. 5, 2. So f of 5 is equal to 2. Okay, here's where things get a little bit different. It was actually with part D, but part C, we found out f of 3 and f of 5. So again, we can just put those two together. We know that f of 3 is 4 and f of 5 is 2, so we could do 2 minus 4, which is just negative 2. So you're not subtracting the x values inside, you're just evaluating f of 5 first, f of 3, and then getting your answer. Okay, the last part, this is where we need to be careful. The value of x such that f of x is equal to 4. This is actually telling us our y value. So if we have our y value, what we want to do is we want to find a point with coordinate 4 for its y value. So start at 4. That's what we're starting with. And well, then what's the x value? Well, the x value is going down. It's just 3. So that is the point 3, 4. Which means x is equal to 4. So then f of 3 is equal to 4, which is what we want. And that's a look at just function notation and how we can make use of it, either with graphs here or just equations from before.